Right, welcome, Andrew. And this is going to be the final lesson for the 91390 series, the CH3.4 standard. So what we're going to do is we'll do that last bit on the thermochemistry calculations, and then we'll just have an overview of everything that's in the standard and points you have to watch out for. So just you're welcome to type in questions at any time, and of course I'll be asking you questions as well. So first of all, just definitions again. You have to know these thermochemistry definitions because you must be able to write the equations based on them. So by the definition, the first one is the heat of formation, delta FH or delta HF. You can write it both ways. The important thing here is it's to form 1 mole of a substance from its elements in the standard state. So for say the delta HF or SO2, you have to have a 1 in front of the SO2, which means you can get fractions when you balance the equation, because this has to be a 1 there. And remember, it has to the elements have to be in their standard state, which means at room temperature and pressure. So sulfur is a solid at room temperature, oxygen is a gas at room temperature. So you would write the equation as given there. The other equation definition you need to know is the heat of reaction, delta RH or delta HR. And as I say, that is for the equation as written. So I could write it with fractions, and then it would be a certain value. If I doubled the value, the delta RH would be doubled as well. So it's always for the reaction as written. So this is for 1 mole of N2 reacting with 3 moles of H2 to form 2 moles of NH2. If I had what would be the difference between a delta FH for NH3 and the delta RH as written over there? I can see you are typing. Right, the product would have to be 1 mole. So instead of having a 2 over here, you would have a half in front of the NH3. That would be 1.5 in front of the H2, and it would be a half in front of the N2. And of course, the value for delta FH for NH3 would be half the value of this delta RH as given. Right, next one is the heat of combustion, and here it's to burn a 1 mole of a substance. So the important thing, it must always be a 1 in front of this reactant. So it's the reactant is always on the left with oxygen. So if I'm saying I'm burning 1 mole of carbon, or 1 mole of carbon monoxide, or 1 mole of sulfur, this first equation is also an equation for the combustion of sulfur, because it's sulfur burning with oxygen. So it's 1 mole reacting with oxygen, and then the products here is the common oxide. So if I'm burning carbon with oxygen, the common product is CO2 and not CO. If it's a organic molecule, of carbon and hydrogen, it's always going to be carbon dioxide and water. So if you're trying to work out a combustion reaction and you get given an organic molecule, the products are always carbon dioxide and water. And you may have fractions because it has to be a 1 in front of what you are burning. Okay, yep. And then the heat of fusion. Now, a common error for students is this F and F for fusion. They often sometimes confuse that and think the delta FH is fusion. Remember, the fusion, vaporization, and sublimation, wherever we have a change of state, it's always 3 letters. So FUS or SUB for sublimation, or VAP for vaporization. So that may be one way to remember. And that's, although fusion, you might think it's a solid forming, it's always from solid to liquid. So it's a change of state, and it's always 1 mole to 1 mole. So the balancing is very easy. Vaporization is again 1 mole to 1 mole. It's where it's going from liquid to gas. And the sublimation, which I haven't put up there because you don't get it very often, is from a solid to a gas. So you have to know those so you can write the equations. So I could say write the equation for the heat of vaporization of water, or write the equation for combusting octane, or write the equation for the heat of formation of Pakistan, of forming octane. Okay, so here's some practice. Because I don't want the lesson to carry on too long, but if you've got a pen and paper handy, see if you can jot them down and then just check your answers against mine. I know I'm going to go through it quite quickly, but the first thing you look at, what is that? So if it's a C, it's combustion. And if it's combustion, what are the two things you've got to watch out for? So when you write this down, there's two things you have to remember. It's 1 mole of sulfur, so you've got to have a 1 in front of the sulfur. Okay, and if it's combusting, what is the other reactant? So one reactant is sulfur, and the other reactant is oxygen. Right, so if I write down that equation, it's S, and it has to be in their standard states. I haven't put the naught in front of there. That always means standard states. So that's why sulfur is a solid, oxygen is a gas, and the common oxide that's formed is SO2. The heat formation for NH3, I picked this one as a comparison for the heat of reaction we had last time. In the previous slide, can you see it's all a half? So it's 1 in front of the NH3, and it's made from nitrogen as an element and hydrogen as an element. Both of them appear as gases at room temperature and pressure, so they are gases. Formation of water, so again, it's got to be a 1 in front of the water. Notice water is a liquid, because at standard temperature pressure, water is a liquid. And so I have a fraction in front of the O2, because I have to have a 1 there. The fusion is for this hexane. It's simply going from solid to liquid. Vaporization is simply going from liquid to gas. And then combustion of methanol. Remember, for any organic product, it's always, whenever we're combusting an organic substance, the products will always be CO2 and water. So there's a CO2 and water. Remember, it's got to be a 1 in front of the methanol. And so when we balance, we might have fractions. Any questions on being able to write formulae based on a combustion, formation, fusion, vaporization, sublimation? Do you think you'd be able to do it? Okay, so say learn those definitions so you remember which ones will have to have a 1. Is it a 1 in front of the reactant or 1 in front of the product? If it's combustion, in front of the reactant. If it's formation, it's got to be a 1 in front of the product. And there's only going to be 1 product for any formation reaction. Okay, so now we're going to use the definitions. And so when we have a heat of reaction, it's always as a reaction is given. So if I make these energy diagrams, here's a case of an endothermic energy diagram. The energy of the reactants, this is really when we form those reactants from the elements, it has a fixed amount of energy. So that's what that fixed amount of energy is. And the energy of the products, it's if we formed those products from the elements, that would be that energy. And the difference between the product energy and the reactant energy is going to be the heat of reactants. So it's always products minus reactants. So in this case, because it's endothermic, I'm going to have a higher product value, so it'll be positive. If it was exothermic, I'd have a lower product value in it, and so it'll be negative. So what we've got with Hess's law is we say, okay, if we're going from reactants to products as in one step, that's a certain energy value. Hess's law says it doesn't matter how I get there from reactants to products, I'm going to have the same total amount of energy involved. So it doesn't matter if I go up, zigzag my way around up the mountain, or if I go straight up a ladder up the mountain, it's eventually I'm going to have the same amount of energy when I get to the top of the mountain, that sort of style. So they give an example of if I have methane and oxygen being burnt, I get carbon dioxide and water, I have got an X amount of energy that's given off. But I could have done that in 2 steps. I could have taken that methane and oxygen and formed an incomplete combustion, in other words, carbon monoxide being formed, and then I could have burnt that further to get my carbon dioxide and water. So it's like 2 steps. And they were saying H2 plus H3 is going to equal H1. So all my little steps will add up to my big step. Is that clear? So, right, so basically if you wanted the long version, it says Hess's law states that the change in enthalpy is independent of the pathway between the initial and final states. So we can add up a whole lot of little steps to get the final step. And it's very useful when we can't actually ever do a final step, because chemically it's not valid, but we could work out theoretically how it could be done. Or if you didn't say I want to burn diamonds, but you wanted to find out how much energy it would be involved, you could work it out using little steps. Okay, now there's 2 ways we can use Hess's law. It depends on the question which one you choose to use. If you're good at writing equations, I like using the long version. If you're good at maths, then use the shorter version where applicable. You don't often have a choice of either or, but sometimes you do. So here's an example of where we'd use the short method. So it's just the maths and we don't write the equations. Now remember, it's the energy of the reactants going to energy of the products. So if I want to find the delta RH of that reaction, I can add up the energy of my reactants, because that'll be down here, and add up the energy of my products, and that'll be up there. And if I subtract them, can you see I'm going to get my delta HR? So these are the reactants in yellow. So if I add up those 2 values, and they are my products in purple, and if I add up those 2 values. So here's my equation that we had met previously, and it's of course products subtract reactants. Now, one thing I want you to notice is I've got a 2 in front of the HCl. So if I have a 2 in front of the HCl, I'm going to have twice the amount of energy that's given there. So can you see there's a 2? I have to multiply that negative 92 by 2. I don't have to multiply anything in front of the H2SO4 because I only have 1 of them. But I do have a 2 in front of the water, so I need to multiply the water minus 286 by 2. So if I do that, I get an answer of negative 62. So it's an exothermic reaction. Now, as I say, it's double check your maths and your calculator, because so often I've seen students write in the right substitution values and then somewhere along the line make a silly error. So just don't just simply write in values and give the answer. Show the teacher how you got there, because then you can see if it's a silly mistake or not. So you don't have to give as many steps as I did here, but write the equation, substitute, and then you can give the answer. You can miss out these 2 steps over here, but I would always double check a reaction. You can also think of, would my values would that be a useful value or correct? Is it a valid answer? If you think of these values over here for the reactants, just think of that's nearly 300. So if I have 2 waters, that's nearly 600, plus say another 300. I mean, I'm just rounding off. So we've got round about 900 over there, and for the H, that's about 100. I need 2 of them, so that's 200. And then we've got 800 over there, so 200, 800, there's a little bit more. So we're expecting to give off more energy. I don't know if that makes sense. So I should have a negative value. But so just use your evaluation of your answer to make sure that you haven't made a careless error. Okay, this is very close, minus 62. It's not like minus 1,000 and something. Yeah, so it gives you an idea, are you on the right track or have you gone wrong somewhere? Okay, so here's now the same thing, but we've, oh, sorry, I'm going to go through all the steps again, and then we're going to do the same thing, the long version. So when you use the long version, it's where you write out every formation or whatever reaction you are given. And you must make sure they're balanced. If you have to reverse an equation, you reverse the sign of the delta H. We've seen how we had to multiply by a factor. So if we had two HCl's, you've got to multiply the delta H by 2. Okay. When you're writing all the equations down, put the equations so that the arrows underneath each other, because you cancel out compounds. So you've got to cancel reactants and products, and it's much easier if you can see which side's reactants and which side's are products. And then I say check, check, check your calculations, whether it's your long or the short version. And then you have to have a unit for excellence, so check that you've done that. And let's now do an example. Okay, it's actually a slightly different one I've given here. So here's an example where I've got to work out the delta HR for this reaction. So I've given you the reaction, so I have to get a final equation being 2ENO plus O2 gives 2NO2. And I'm given two equations. Okay, so the first thing you do is you look at the reaction, you go, well, okay, this is my final reaction, so I've got to have NO2 on the right hand side. Okay, and where's my NO2? It's also on the right hand side. What is different between these two NO2s? The coefficient, correct. So I'm going to need twice as many of this last equation, and I've got to double the 33 to make it match the 2 over there. Okay, so I was highlighting that. Then look at what must be on the left-hand side of the equation. I've got to have NO2. So you look at the given equations and you go, NO, sorry, I've got to have NO there. So I've got 2 and 2, but what is different between these NOs? So I can see you have the side of the equation. So I've got to do what to this given equation here? What must I do to it to get it to the left-hand side? I have to reverse it. And if I flip this around, so the NO is on the left-hand side and the N2 and the O2 on the right-hand side, what do I need to do to the 183? I have to change the sign. Okay, and then finally my oxygens are fine. They're all on the left-hand side. You will notice that I've got more oxygens on the left-hand side here than there, but that's not going to be too much of a problem because we know we're going to be doubling and flipping, so it could all cancel out. The single molecules like O2, H2, N2, those normally cancel out without a problem. So now let's look at that first one. Remember, we had to flip this equation. So can you see I've flipped it? There's this big gap that I've left here because I want all my arrows to be underneath each other. So I flipped it. I didn't have to multiply anything by a factor, but I did have to change my sign. Now, the next thing I have to do is that second equation. I don't have to flip it, but I do have to multiply everything by 2, and I should have put that in red as well. You can see I must multiply the 33 by 2 as well. Now I check, does everything cancel to leave me with the equation I want? So I've got N2 on the right hand side, gas, and I have got 1 N2 on the left hand side, because 2 times a half is 1. So the N2's cancel, which is great. Then I have got 2 oxygens on the left hand side and 1 on the right hand side. So the right hand side will cancel out 1 of the O2's on the left hand side. So I'm left with 2NO, I'm left with 1 O2, and I'm left with 2NO2 that hasn't cancelled. And you check, does that match my equation? Thank you very much. Does that match my equation that I want? So you just double check that, and if it does, now you just simply add these values up. So negative 183 plus 66, and that should give you negative 117 kilojoules per mole. Check that you've put the unit down. Okay, quite simple. Do you think you should be able to do it? Right, okay. The trick is, of course, check that you haven't made careless errors. That's I'd say the most common error is some sort of transcription error, either in writing something down or in your calculation, something dumb gets done with a calculator. So here's another example. Here we've got so the first thing you do is you find out what do you need to calculate. You were given the equation last time. Here we're not given the equation, we're just simply told you've got to calculate the heat of formation of hexane. So work out your final equation so you know what you've got to aim for. Now I chose this one because I wanted you to see what carbon is in the standard state. Because carbon has lots of allotropies, you can't just say solid, because it could be diamond, it could be graphite, it could be lonzolite, it could be all sorts of things, but the common one is graphite. So that's what we use. Remember, the formation is 1 hexane from its elements in the standard state. So once you've done that, you now look at the given equations. So you aren't given actually equations here apart from this one, which is a combustion of hexane, but you're given the value for the formation of carbon dioxide and you're given the formation of water. So here's the equation you would work out for carbon dioxide. Remember, 1 carbon dioxide is 1 graphite and 1 oxygen, and the formation of water is 1 water from hydrogen and oxygen gas. Now we manipulate, we swap, and we see what we need to do to get to that final equation. So we want hexane on the right hand side, we want hydrogen on the left hand side, and we want graphite on the left hand side. So the first thing we look here is hexane here is on the left hand side. I'm going to have to reverse it to get it to the right hand side. The next thing you're going to look, when you look at this equation, I need carbon. So it's on the right side, but I need 6 of them, and I've only got 1. And then finally, I need H2, and that is on the correct side, but I need 7 H2, and I've only got 1. So now we just write them down, starting off with the graphite, going to carbon dioxide, and all I do is I multiply everything through by 6, including the delta RH. That should have been the heat of formation. Okay. Then the next one is the heat of formation of water. I do everything, but I multiply through by 7, and 7 times a half is 3.5. That's where that value comes, and 7 times the heat of formation gives me that value. Now the final thing is the given combustion one, and I had to swap that around, but I didn't have to multiply it by a factor, so I just swapped it around, and that's where that negative comes in. I had to, although it was a negative value, I had to reverse the sign again, so negative times a negative makes us a positive. Now I cancel out, so my 6 carbon dioxides cancel my 6 carbon dioxides. My 7 waters cancel my 7 waters. My 9.5 oxygens cancel 6 over there, and 3 over there makes 9.5 on the left hand side. So I'm left with graphite, 7 water, 1 hexane, and So that is the equation I want. Always double check that it is the equation you want. And now you just simply add negative 2358 plus negative 2002 plus 4163, and you get a negative answer. Again, double check things. You're quite right, these should have been heats of formation. I had it correct over there, but I put R over there. Reaction is still okay because it's a reaction as given, but it's it was the formation value that I was using, so it wouldn't get marked wrong if you put R there. Okay, so again, use your sense of evaluation. Is that a reasonable answer to get? Just to make sure that you didn't make a silly error somewhere in your calculator. Okay, so here's now the same problem, but we're going to use the short version. And by short version, I mean using this delta RH is product subtract reactants. Now what we've got here is the delta RH we're going to use here is what we are given over there. So that value minus 4163 is going to be our delta RH. And then our products is going to be this, and our reactants is going to be that. Simply because, remember, it's the heat of formation of the products and the heat of formation of the reactants. So that hexane that we're looking for is going to be in our reactants. It's going to be sitting in over here. So I've spelt it out now. Can you see the sum of the products? So it's carbon dioxide and the water, because those are products, and then the formation of our hexane and of our oxygen. Now, if I'm forming oxygen from its standard state, if you think of the equation, if you had to write out the equation for oxygen, forming oxygen from its standard state, what would it be? Okay, no. It's basically, remember, I'm forming one oxygen molecule, so it's going to be one O2 on the right-hand side, and I'm forming it from its element, from the element, which is oxygen, in its standard state, which is a gas. So it's basically going to be O2 gas going to O2 gas. Is there any change if I go from O2 gas to O2 gas? No. And if there's no change, the energy is going to be zero. Because it's not changing, I'm not going to have any change in energy, so it's going to be zero. So whenever you have a formation of an element in its standard state, it's always going to be zero. Okay, so that actually R should have been F. I obviously wasn't looking properly, and that is going to all be zero. And of course, 9.5 times 0 is also 0. Yes, and I should have also put a 0 up there, delta H naught up there. Yeah. Okay, and that's what I've got there. The delta F, well, I have it right here for O2, is 0 kilojoules per mole. And because it's O2 gas going to O2 gas. Yes, hydrogen, if I was forming hydrogen, H2 gas going to H2 gas means I'm going to have a 0 change. So the value is 0. So now I just have to plug in the values here. So the minus 4163, remember that's for, for our reaction. Sorry. So that goes on the extreme left. Remember, I've got 6 carbon dioxide values, so I've got to put it in. I've got 7 water values, so that's got to be put in. And now I subtract my reactants. That's my unknown that I'm looking for. That's what I'm calculating. And of course, any element in its standard state is going to be 0 no matter how many there are. So 9.5 times 0 is 0. Now I just simply work through the maths. So what I've done here is I've moved the equal sign over. In other words, I've taken this and moved it across to the other side of the equation, which means if it was positive on this side, it becomes negative on the other side. And what I then do is I want to change that to a positive value, so I multiply everything through by negative, so that becomes positive, that becomes positive, and my negative over here becomes positive. And I've multiplied these out so that you get the values there. And now I'm just rearranging so that appears on the left-hand side of the equation. So it's straightforward sort of algebra maths. And I say 4163 plus 41. I made a mistake. Sorry, that should have been 2358. My apologies, 2358 plus negative 2002, and I should get to the same answer. So you've seen the version where it's lots of equations, and you've seen the maths version. So I'm just going to go previous. Let me just go to slide. So here's the one where it's you write a whole lot of equations, and here it's where you write the maths. Which one do you prefer? Okay, you're typing the product's reactants, and that's fine. You decide which one. Sometimes you don't have any choice because of the way they don't give you heats of formation, they give you combustion and reactants and all that sort of thing. But wherever you get given heats of formation, you can choose the short method. Okay, right. So here's another example, and here I have given not the formation, well, that you could see as a formation, the CO2. That's a formation of water, but this is not a formation because I don't have just one substance on the right hand side. So I can't do a straightforward or short method unless I did it like the last one, because is this a formation up here? Remember, you can recognize a formation. Yep, it is. If it is only one substance on the right hand side and it's the stoichiometry is 1 or the coefficient is 1 and the left hand side is only elements in its standard states, then you know this is a formation. So you could do this the long way or the short way. Okay, so I think I've done it the long way here just for more practice. So what I've done here is I go, right, I need to calculate the enthalpy for this. So I need the graphite on the left hand side, but I need 2 of them, so I've multiplied by 2. Here I need the hydrogen on the left hand side. I only need 1 of them, so I don't change anything in this one. And now that third one is to give me the ethine, the C2H2, and of course that's on opposite sides of the equation, so I have to reverse the sign. Reverse the equation, reverse the sign. And I don't have to make any other changes because I only wanted 1 of them. And now you cancel, and you are left then just with exactly what you want. And as I say, always double check the equation that you got what you're looking for, and then do the calculation. So they're quite straightforward. You've just got to double check so that you don't make a silly error. Normally it's from transcribing. Okay, we've now done everything in terms of what will be in the standard of these last 6 lessons. So what we're going to do now is go over an overview. So it's what NZQA puts out for the teachers, and we'll look at the standard to see what comes up in the standard. So this first bit about resonance, Hund's rule, and so on, you'll know about it probably from university. And if people were Googling things, they might come across these concepts. They will not be examined. And it also tells you that in the exam you will always get the value for the heat capacity of water. Remember, you needed that for calorimetry questions. You will always be given a periodic table. And although you're not given this sheet in the exam of called the quantities, units, symbols, and nomenclatures in chemistry in that reference sheet, it won't be given in the exam. But if you want to know how you're supposed to present something, you know, the symbols, nomenclature, and so on, you can look it up. Now, I haven't provided it to you because all the booklets follow those conventions, but if you want to look it up, that's how it would be presented in the exam. They'd follow all those rules. Now, the important thing is, and I've said this before, you are expected to calculate molar masses where needed, so they won't necessarily provide. It says it could be given with the question, or they expect you to work it out. So just because you're not given a molar mass doesn't mean to say you don't need to use it. They expect you to be able to work it out. And then this is really important, that you show all working calculations. I don't think you can get excellence if you don't show your working. Okay, and I'm not too sure about achieved. And then for excellence, it's really important you round off to 3 significant figures. With the ones we've just done with Hess's law, it's not important because we're just adding or subtracting. We are not multiplying. And remember with adding and subtracting, we go by the number of decimal point values. So it's only when you're multiplying, so when you're applying n is equal to small m over big M, or C is equal to n over V, or the calorimetry one, where you're multiplying, that's when you need to round off to 3 significant figures. You don't round off for Hess's law stuff, because we're just adding and subtracting. Is that sort of clear? Okay. And then for excellence, you need to have the correct units. If you don't have the units, you won't get excellence. I think you're allowed 1 slip up. Okay. Right, so this is now what's in the standard. So if you went to the NZQA site and you looked at the standard, this is what comes up. So it says it's the properties of particles, and so you must be able to do electron configurations of atoms and ions for the first 36 elements with the SPD notation. And so what is important here? You've got to learn the exceptions for copper and chromium. So it normally follows the sort of rule of the periodic table, where you just follow along, okay, the S block, the D block, the P block. But remember, copper and chromium, because of the full d orbitals or the half d orbitals for copper or for chromium, it's 4s1 3d10 or 4s1 3d5 for the chromium. So learn those exceptions off by heart. The next trick you've got to remember is if you've got a cation, if it's just any old cation, you can just simply subtract those electrons. But if you've got a transition metal cation, like copper 2+, you have to remove the 4s before the 3d. So can you see we didn't say 4s1 3d8 for copper 2+. We had to remove from the 4s first, because that's the valence shell. It might be higher in energy, lower in energy than 3d, but it is the outermost shell. It gets lost from there first. Okay, and then as a final check, that's why I like the long method, but you're welcome to use the noble gas shorthand method, is count the number of electrons that you've got in these superscripts and check on your periodic table for the atomic number. So copper has atomic number of 29, so you should be able to count 2 plus 2 plus 6 is 10, plus another 2 and 6 is 18, 19, plus 10 is 29. So add them up, because you'd be amazed at the number of careless errors. You're in a rush, you're under pressure, and you can just write a wrong value. So add it up. Spend that little extra 30 seconds adding up. The next thing that comes up, okay, that's pretty much an achieved level question. So you guarantee to get a question on it, but it'll be roundabout achieved. Okay. The next one, this is where the merit and the excellence comes in. It's the periodic trends. And it's really important that you give enough detail in your explanation. As I say, shorthand, think of pens, rhymes with trends, pens, protons, electrons, energy levels, effective nuclear charge, everything starting with E, N, nuclear charge, D, distance from the nucleus. Okay, so is it the bonding electrons distance from the nucleus or the valence electrons distance from the nucleus? If you're thinking of electronegativity, you talk about bonding electrons. If you're talking about ionization energy or radius, you would be talking about valence electrons. And then S for shielding. So make sure you discuss those for each one. So if you're going about across the period, discuss all those 5 points. If you're going down the group, you discuss all those 5 points again. Don't just say, oh, it mentioned distance in the first one, so I don't have to mention distance again in the second one. So you have to do it for both, otherwise you won't get excellence. And then remember, always include your states. If you were asked to write ionization energy, if you don't have the states in, then it's going to be marked wrong. You've got to have the states. Okay, then next one up is Lewis structures and shapes and polarity. And this is again a merit excellence type question. You have to give at least 1 point for achieved, and that applies even to the trends. If you just simply said the electronegativity increases across a period and decreases down a group, you're not going to achieve. You must have at least some explanation. And the same thing here. So points to remember, Lewis structures, the first thing you do is always work out your valence electrons. So you look at the element in the molecule or ion, see what group they're in, and then say, okay, if it's in group, say it's xenon trioxide, XeO3, xenon is in group 18, so it has 8 valence electrons. Oxygen is in group 16, so it has 6 valence electrons. And because I've got 3 oxygens, XeO3, it'll be 3 times 6 plus 8. And that'll be the total number of valence electrons. And once you've drawn your Lewis structure, check that you've made enough dots. Because a common error is, say if I had, let's take an easy one, CH3F. People forget to put the non-bonding electrons around the F. They'll put them between the C and the H and the C and the F, and they'll forget about the lone pairs. So count your dots at the end and see if they work out to be the total number. Okay. The other thing is also, remember, if you've got a molecular ion, then make sure you put in the square brackets and the charge. So by molecular ion, I mean if you had Cn minus or something like that, NO3 minus, put in those square brackets and the charge. One other thing about Lewis structures that I haven't put here is with Lewis structures, when you've got an acid, say H2SO4, where are the H's bonded to? Are they bonded to the S or are they bonded to the O? To the O, correct. So you could be given phosphoric acid, H3PO4, sulfuric acid, H2SO4, sulfurous acid, H2SO3, nitric acid, HNO3. Remember, the H's are always bonded to the oxygen and never to the central nitrogen, phosphorus, or sulfur. You could be given the ions as well. So I could give you HSO4 minus. So remember, the H is bonded to the oxygen. Or HPO4 2 minus. Remember that the oxygens are bonded to the phosphorus, but the H is bonded to the oxygen. So learn those acid ones. They often come up. I can't say they're guaranteed to come up, but they often come up. Either the full acid or an ion of the acid, like HSO4 minus. Like shapes, the important thing with shapes, the first thing you have to talk about is the electron density, the number of regions. So electron geometry, what is the shape of, in terms of the electrons? So if I've got 5 regions of electron density, my electron geometry is trigonal bipyramidal. If I've got 6 regions of electron density around the central atom, it's octahedral. So always start with that first, and then say how many lone pairs or bonding pairs I've got of electrons. So if you get asked, what is the difference, why is the shape different between IF3 and NF3? Don't just say IF3 has got 2 lone pairs of electrons and so will be different because nitrogen has only got 1 pair. That might give you an achieved, okay, perhaps, but it certainly won't give you merit or excellence. You would have to say IF3 has got 5 areas of negative charge or 5 areas of electron density around it, giving it a trigonal bipyramidal shape. NH3 has got 4 areas of negative charge around it, giving a pyramidal shape. But in NH3, one of them is a lone pair and 3 are bonding pairs, so the molecular shape is trigonal pyramidal, and the IF3, because it's got 2 lone pairs and 3 bonding pairs, the shape would be T-shaped. So can you see how you would work it out? Always start from the total number of regions of electron density. Okay, and then with the polarity, it's important for excellence to always discuss electronegativity and show that you know your trends. So if you've been given IF3, fluorine is higher up in the group than I, so you should be able to say that fluorine has a higher electronegativity than iodine. Don't just say there's a difference in electronegativity, just show that you've understood the trends, and you can use the periodic table so you can work out which ones are different. So difference in electronegativity, then you talk about the bond dipoles, and then you talk about the symmetry of the molecule and whether those bond dipoles cancel out or not. So it's important you talk about all 3. Okay, so we're nearly done. Attractive forces. This is where you have to talk about the permanent dipole force of attraction, the temporary dipole forces of attraction, and the hydrogen bonding. And you must talk about all 3. Hydrogen bonding, I've just been marking a few more, 3 or 4 twos and so on. Use a diagram to say what you mean, because I find students get very confused in their wording. They know exactly what they mean, but if somebody else was reading their words, it can be quite confusing. So draw a diagram and label the hydrogen bond, because I find a lot of people will say something like, ethanol's got hydrogen bonding because it's got an O bonded to a hydrogen. Now that doesn't say very much. You might know exactly what you mean by that, but to another person it doesn't mean much. So a diagram is really worth it. Also remember what affects the size of the temporary dipole and what affects the size of the permanent dipole. So permanent dipoles, it's only the size of the dipole. So the bigger the molecular dipole, the stronger the permanent dipole force of attraction. What affects the temporary dipole force of attraction? There are 3 things that affect the temporary dipole force of attraction. The size of the molecule, correct? And by size, it's also meaning the number of electrons. Okay, not too sure. The mass, okay, that's related to size, but if we mass, you could argue with mass by given the molar mass. Mass does have an effect if we were comparing isotopes though. And the other one is shape. So is it a long, thin shape or is it a round, fat shape? So that the shape doesn't affect the permanent dipole force of attraction. It does affect the temporary dipole force of attraction. Okay, the shape will only affect the permanent dipole in terms of if it's polar or not do the bond dipoles cancel. But once we've got a molecular dipole, the shape doesn't matter. Okay, right. Now the final things were in the 3043, which is the we looked at entropy and the calculations. What we talked about in terms of the intermolecular forces, you must be able to use them to explain the melting point, the boiling point, the solubility. You must be able to say whether a reaction is going to work or not. Is it going to be spontaneous based on enthalpy and entropy? Okay, so sorry, that was when you're discussing melting point, boiling point, solubility, you must talk about all the permanent dipole force of attraction, the temporary dipole force of attraction, and the hydrogen bonding. Don't just go for what you think is the biggest one, talk about all of them. And remember, you can be given boiling point or the vaporization energy when you have to explain the different types of intermolecular forces. And then remember, always state that the entropy change must be positive for a reaction to be spontaneous. That's a sort of standard statement to give you an achieve level for that question. And then you can build on from that. And then what we did in this lesson and last lesson is the definitions. Remember, there are two types of calculations, the Hess's Law one, short version or long version, and then of course the calorimetry one, which we covered in the last one. So whenever you see a specific heat capacity, you know you're talking about calorimetry. And then, as I say, final thing is don't forget the units. That's it. We've now done everything for the 91390. Do you have any questions?